Welcome to this brand new chapter on normal distribution. You are left with 3 more chapters until the end of the whole syllabus. So S3, S4, S5, and then S6 lah. So 4 more chapters. This chapter is a continuation of the previous chapter. So in the previous chapter, we talked about discrete random variables. So now we're going to be talking about its sibling called continuous random variables. So by this point, if you're watching this, you probably have your lecture notes in school already, and all the technical stuff, the very complicated stuff is all in there, right? So I want to just use this video opportunity to explain to you the concept, the whole idea behind this, and give you a easy bridge from what you already know to what you don't know yet, right? So I'm gonna build that bridge for you right now. Okay, so let's talk about what you already know, which is in the previous chapter. In the previous chapter, we talk about this thing called the discrete random variable. And as the name suggests, there are 2 different parts to this variable. First thing is that it took on discrete values. So values that I can count, right? For example, a value of 1, 2, 3, 4, 5. They are discrete, right? There is 1, 2, 3, 4, 5 like that. And the second quality about this variable is that it is random. So there is a element of chance associated with each variable, right? For example, if I took on the value 1, right, there is a 1 out of 5 chance that I took that, right? And then there's another 1 out of 5 chance I take this value, and there's another 1/5 chance that I actually take this value over here, right? So that is what we learned in the previous chapter. And of course, if I were to write big X equals to this, and then probability of X equals to X over here, right? You know that what I've just drawn over here is your probability table, right? Your probability distribution table, which is what you learned in the previous chapter already. So now bridging to continuous random variable, breaking down the name continuous random variable. The word continuous suggests the idea of a range, right? This variable takes on a range of values. So for example, the height of students in a class, right? Your classmates, your own class, you have a range of heights, right? From the shortest student to the tallest student, right? And the thing is that when it comes to height, the values of your height is not exactly 150 cm or it's not exactly 160 cm, right? Most likely your height is 150.12348 cm. Like, we will never ever be so specific, right? So the value is not discrete per se, because number one, I cannot directly pinpoint at that value and say that I'm very confident that you are 150 cm because you are 150.12348 cm, right? Your value is never certain. And the second thing is that the height of the students in your class, they vary across the range. It's not like the next person is 150.2 cm, right? And even if it's 0.2, we can also argue that it can be 1.14 or 0.15, right? So the values are just not exact in that sense. That is why for this type of variable, we have to have a different way of representing the probabilities. Because again, since it's random, this variable can take on any value within the range, right? So if I were to combine the 2 definitions above, this and this, the variable can take on within the range. So if let's say I tell you that the range of the students' height in my class is from 150 to let's say 190, and then I tell you that your height is here, right? Your height may be 160.1234567891234 ... right? If you want to be really, really specific. So we cannot really directly pinpoint that height is your height, right? So how do we actually represent all of these probabilities? So that is the first concept that we're going to be talking about. For discrete random variable, we are able to represent the probabilities pretty easily. This is how we represent the probabilities. But for a continuous random variable, the way that we actually represent the probabilities, so represent the probabilities, is through this thing called a probability density function. Okay, so that's the first thing that you need to know. We represent it through this thing called a probability density function. Whereas for above, this is your probability distribution table. Okay, so one is a table and one is a graph. So this function over here, right, the formula is actually out of your syllabus. You don't need to know the formula. And in fact, the formula is actually very, very, very long and very, very complicated. Even I myself don't really remember it because it's just so complex. But what you need to know is not the formula, but rather is how we actually do calculations with the formula. Because your calculator, your GC, already has the formula in it. So you don't need to memorize the formula. Neither are you required to write down the formula because it's very long. But what you need to do is to know how to manipulate your GC to use the formula to actually calculate things. Okay, so the graph actually looks something like that. So because we don't need to know what the actual formula is, so from this point onwards, we will just call it fx, right? We will just call it fx from here onwards. And the shape of fx actually looks like that. It's more or less like a bell curve, right? It can be skewed to one side, it can be skewed to the other side also, but more or less the shape is usually like a bell curve. Okay, so I'm just going to draw a very symmetrical bell curve over here. So this vertical axis, right, this is the probability density, whereas the horizontal would be the values or range of values. I would say the range of the values. So for instance, let's say I want to know what is the probability of someone in my class having a height of lesser than 160 cm. Okay, so if I were to contextualize it, for example, let's say what is the probability of someone in my class having a height of lesser than 160 cm. So if let's say I look at my range of values and then let's say 160 cm is over here. Right, this is 160 cm. That means the probability of 160 is here, right? And then let's say this has some sort of arbitrary value over here. And when we say the height is lesser than 160, that means we want to also include those who are like, for example, 159, 158, 157, and so on and so forth, right? All of them are included inside this range. So the probability in this case will be represented by the area under this graph over here, right? Because this graph is the probability density. So at every value along the range of values over here, they have their own associated probability density, right? For example, 160 cm has this, imagine 160 cm owns this line, right? Then imagine 159 owns this line. Then imagine 158 owns this line. Then 157 owns this line. 156 owns this line. 155 owns this line. 154 owns this line. 153 owns this line, so on and so forth, all the way to the end, right? So when we take the individual lines and then we add all of them together. When we add all of them together, it's as good as finding the whole area under the graph. You think about it. When we add all the individual lines together and knowing that all the individual lines are literally side by side because we want anything that's below 160. So 159.9, 159.8, 159.7, right? They all have their own individual lines. And then when we add all of them together, we effectively get the whole area under the curve over here, right? So that's the difference between this and the top, right? The top is very straightforward. We know the exact probability, but whereas for this, we are actually trying to find the area under the curve, right? So effectively, this one would be the probability that we want to find. And since this is area under the curve, right? Area under the curve, the concept behind this is actually your integration, right? Let me just change this over here. And then let's say I want to find the height between 150 to 160. So imagine, let's say 150 is here. So what I'm actually integrating on my curve would be lower limit is 150, upper limit is 160, and I'm integrating fx with respect to this axis over here. So that is your probability density function. So once again, you don't need to know the function, you just need to know how to use your calculator to derive the area under this curve. So essentially this whole chapter is just using your calculator to calculate the area under this curve. That's about it. But as for starters, you need to know the concept behind this. Okay, and as of this point, I will summarize for you before we actually proceed. Right, I will summarize for you a few key important things that you need to know before we actually try to practice on a question later on. Okay, so I'm just going to zoom in over here. So the first thing would be for this graph over here, right? When I integrate the graph, assuming that we take the biggest possible value of the range, okay, and I'm just going to call it infinity, right? Because effectively, this graph, you can imagine it as extending all the way lah. So hypothetically, it can extend all the way. So I'm just going to put infinity over here to show that we are taking the extreme end of the range. And then if we go all the way back, right, for this over here, if we go all the way back, we'll take the extreme end of the range over there as well. So hypothetically, if let's say I take the extreme end and the extreme end over here, and I find the whole area under the graph. So effectively, when I'm just trying to find the whole area underneath here, right, if I do that, the value is 1. Okay, so the thing about this is that the whole area under the graph will always add up to 1 unit. So for most of the questions that you will do in this chapter, the answer is typically decimal to 3SF. And the second thing is that the probability density of anything will always be bigger than or equals to 0 for all real values of x. So for all real values of x, that means the probability can never be below 0, right? I mean, it's just like your usual probability common sense. It cannot be below than 0, but it can be 0, right? So that's that for that. Okay, before you start doing this question, I must clarify one thing first. Okay, so usually the question will not tell you what is the function, right? Usually the question will not tell you the function. But in this case, if the question is the probability density function, right? If it gives the function over here, then we will follow the function that they give. So the context is king. Okay, that's number one. And since context is king and they give the probability density function, that means we can no longer assume it's a bell curve shape anymore. Okay, so this one is when they give us the function. So now we just need to follow what the question gives us to actually solve it. So that's it. Pause this video right now to try it out, and when you're ready, you can come back and unpause this video and let's go through the answers together. All right, so let's go through this question right now. Even though I did not mention any formulas whatsoever, right? But the thing is that based off your understanding of expectation and variance from the previous chapter, you should be able to do this question pretty easily as well. Okay, let's sketch the graph of fx first. So for part A, this is my y-axis and then this is my x-axis. So the headers for the axis is still the same, right? Over here, this one you will just write your probability density will do, and then over here this one would be your values of x, right? So it's just be x, your values of x over here. Actually, you all also can write fx, right? Because fx is just your probability density, so you can write either one of them. So from 0 to 10, when x takes on the value of anything from 0, so up until 10 over here, let's put 10, right? And then we know that 1 2 3 4 5, right? They're all in the middle, but you don't need to write that. It takes on a constant value of 1 over 10. So taking on this constant value of 1 over 10, that means over here I'll write 1 over 10, and there will be a constant value until here, up until this point over here. And then anything afterwards, it will actually go down to 0. So after that, it will go down to 0 like that. There's a sharp drop at 0 over here. So this is essentially the graph. Okay, it's not a curve, it's a graph. But as I mentioned earlier, if they give you the function, then you have to contextualize it. And in this case, it's clear to see that it's no longer a graph, right? So now that's that. That's done. Now B, find the probability that the waiting time is less than or equals to 3 minutes. So over here, just want to preface that how do we actually read this probability density graph? So we have values from 1 to 10, right? Okay, I'm just going to write out the 1 to 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And each of these values over here, so let's say this here, right? They all have a probability of 1 over 10. So if we want to find the probability that the total waiting time is less than or equals to 3 minutes for part B, so probability that the waiting time is less than or equals to 3, what we are actually trying to do is that we are trying to find the area under the graph from 0 to 3, right? And this is of fx over here, dx. We are essentially trying to find out what is this whole area under here. And luckily for us, this is a rectangle, right? So this being a rectangle, it's a lot easier for us to calculate it, because from here onwards, we can just simply take 3 times 1 over 10, right? Length times breadth, because this is a rectangle. And then in the end, we end up with 3 over 10 as the final answer to this question over here. Okay, so just trying to show you how to read a probability density graph at this point. Okay, now C. What is the expectation of x? So the expectation of x, based off your understanding from the previous topic, right? The expectation from the previous topic, I'm just going to write here, from the previous topic, it will be the sum of all the x values, right? X times the probability associated with them over here, right? We just want to find out what is the expected average value of x in the long run, essentially. The idea never changed, but now it's in the context of a graph. So in the context of a graph, now we are trying to take the x value, right? Multiply with 1 over 10. Because the probability associated with each x value is 1 over 10, right? And this x value over here, it ranges from 0 all the way up until 10. And then I'll put a dx over here, right? So I'm just going to do it. I'm just going to annotate my working here. 1 over 10. The probability is constant, 1 over 10 over there. And then we are trying to take all the individual x values. So all the individual x values with this from 0 to 10, from 0 to 10 over here. And we are essentially trying to find out what is the value that we get at the end, right? So when you integrate tan 0 x over 10 dx, right? You do your simple integration, you get that the value over here is 5, and that's the final answer to this over here, right? And last but not least, you have variance. So again, variance, from the previous topic, you learned that it is the expectation of x squared minus the expected value, and then you square it, right? So it's the same logic here once again. This value you know is 5, so what happens if it's x squared? The formula still remains the same, right? It's just that now we square the value first. So we are taking the range of values of x from 0 to 10. Now instead of x, we have x squared multiplied by the constant probability of 1 over 10 dx. Then from here, our minus 5 squared, right? And then when you compute this definite integral, the final value that you get at the end is 25 over 3. And that's the final answer to the last part of that. All right, so we have not gone into the nitty gritty of this chapter yet, but so far whatever we have gone through gives you a good idea, I hope, of what this chapter has to come and what to expect in the upcoming concepts. Okay, if you've got any other questions, feel free to leave in the comments below. Otherwise, I'll see you in the next video.